Very good afternoon, all students. Welcome back to the Institute after Diwali holidays. I'm sure all of you have got a better energy now after 1 week's refreshing holidays and you enjoyed Diwali. So before Diwali, we have started talking of dynamic programming and we have discussed MCM, matrix chain multiplication problem, and we have systematically understood all 4 steps which we used for solving a problem, starting from its characterization of optimal solution and up to final DP solution. So that we applied. And today we are going to continue this, but now you could see that I have today a normal pen and paper to write. I'm sure this will help me as well as you in better writing and better understanding than digital writing pad, which I was using earlier. So let's see how is this experience, and maybe accordingly we can change later, but I'm sure this will probably be a better experience. And share your feedback and accordingly I'll readjust. So after going through the MCM problem, I think it's the time that we revise the concepts and use it for some more problem solving so that you get more confident and learn more. And today we are going to see something related to DNA matching. Well, don't be surprised that why we are talking of a DNA matching, why we are going towards biology. Of course, DP will come into picture at a later stage. But as all of you are aware that there are primarily DNA consists of 4 bases which are used. I'm just using their abbreviation, not going into more detail of biology. But yeah, I know sequence of these bases becomes one DNA. And these 4 bases which are used are these AGCT in an abbreviation. And how do we match? In movies, we see a lot of matching being discussed. We find a lot of fictions and a lot of murders and other issues being solved through DNA matching. Some of those could be true. Some of those could be scientifically may not be feasible now. But yes, definitely algorithms play a crucial role in DNA matching. Let's assume if I know some DNA, for the time being, I will simply convert it. Let's say I'll use it in form of say ABCD instead of saying AGCD. So AGCT, so I'll say, let's say we have some ABCD basis that effectively leads me that I will treat everything as a string, and basis of the DNA are named as ABCD alphabets or AGCT, one and the same thing. So treat them as some normal alphabets, and we are choosing to do that. Well, how do we match? So there could be many ways to finding similarity, that whether DNA 1 is similar or DNA 2 is similar or not. Let's say I'm given one X DNA, first DNA, and I'm given Y as another DNA. So are they matching? How much similar they are? How do I know? So obviously, one criteria of that can be finding whether somebody is a substring or not. So X being a substring of Y or vice versa. So both possibilities can be, if they are somebody is a fully substring of someone, obviously it is a similar match or it is a similarity. But if not, does that mean there is no similarity? Yes, definitely not. So we cannot say only substring can be this. But yeah, substring, you know, str function in C programming through which substring can be compared, or substring can be checked whether it exists or not. Similarly, strcmp also you might have used, but they might not be mostly completely suitable. So you can see string matching versus DNA matching have a lot of similarity, and that's why we are talking of DNA matching being attempted this. Second, normally DNA, we say that how many changes are needed to convert one DNA to other. How many changes needed? That can be another way of finding the DNA matching. How many changes needed to convert X to Y or vice versa, to convert, let's say, X to Y or maybe Y to X. For example, if I say I have, let's say, A, B, C, B, A, D, C, A as one, other one being, let's say, B, C, D, A, B, C, A, and let's say B. Now, these two, I don't find anybody to be substring of some bird. I don't find exact equality. Are they not similar? Maybe one answer, yes. But if I see carefully, probably I can find a lot of match in this form. So effectively, I could say conversion could be possible that let's say this converted to null, then no change, B converted to D. So I say convert A to dash, no change, B to D, then again no change, A to A as it is, D to D as it is, C to C as it is, A to A as it is, and then dash to conversion to B. So if I see only 3 changes needed, in fact, out of length of 8 or 9. So I could easily say that out of this length, only 3 changes could make DNA this to be there. Why? I'll say that instead of writing the way it was earlier written, I could have probably written, let me just remove this. So, okay, I have to probably go to other side so that, right. So if I say I had A, B, C, B, A, D, C, A, I could easily write it in a way that just try to write it by shifting towards right the second string by one place, and effectively I am able to directly have one-to-one matching at most of the places, not this, but all other places. So I can easily see a lot of similarity is visible. So that can be another way of finding similarity. So there are different possibilities to do that. Similarly, the third similarity, which is more useful to us, is called as common subsequence. Common subsequence, effectively meaning to be called as common subsequence. Say longest will be obviously what we require to find, and in general it is called as LCS. And now I connect DNA to my DP because LCS solution is a DP problem and a DP solution is possible to this problem. So longest common subsequence means we should find the subsequence which is common in both. And what do we mean by subsequence? That we will understand. So I want to know the subsequence which is common in both X and Y. What does that mean? For example, I say if I have a string X as A, B, C, D, B, A, C, B, and I have Y equal to, let's say, D, C, B, and maybe A, B, D, A, B. So I could say out of this, if I try to find some similarity, I could say maybe A, B, let's say here I have A, D, B for a change. So I say Z can be the answer, which can be one common subsequence. Common subsequence can be something like, say, I claim it to be B, D, and B, D, A, and maybe B, at least one this. Why? I say, what does common mean? B is here also, D is here, A is here, D here. Similarly, I say B, D, A, B. So this is common in both. So what are, and of course, may not be longest, but this is common. So we would like to know the common subsequence, may not be longest. Of course, we want longest, so I'll say find longest one. For example, in this case, I could say that C, D, and then maybe A, C, B, that could be a longer sequence. Why? I can see C, D, A, C, B. Here also I have C, D, A, C, and B. So if I have this sequence, I can claim that these are available with me. So this can be the probably longer one, length 5. So effectively, it means that I want to find Z as a strand, as a thread of the some length, such that all bases in Z are present in X as well as Y in the same order but may not be consecutive. May not be consecutive. As you could say, consecutive will mean they have to be exactly in sequence of that data, but now I don't have those as in consecutive order. So I'll say this is going out of screen, so I'm just writing it may not be consecutive. So, for example, CD, A, C, B, I could easily see appears in this order in X as well as a Y, appears in this order in X as well as Y. So this could be one possibility of the answer. And maybe can we find longer than this? Is it longest or not? We are not sure. So, but this is what we mean DNA matching. And such a problem, if to be solved, obviously you can see this will be an exponential solution possible. How to solve this? How to find such matches? So this is third kind of a match, which is known as LCS matching, but exponential solution will exist to this problem. Why do I say exponential solution? You can easily see that how to do this. Obviously, I say if full X, say length was M, if that is present in as it is in Y, say length of Y is N, then I will say M is the longest. But if M not present, maybe I'll say find subsequence of X with length M minus 1. So next minimum length or next level of length. And if any of this exists in same order, any of this is present in Y, then I can definitely stress. So if any of this is present in Y, obviously I will say length of LCS will be M minus 1. If not, then I will say find X with the length M minus 2. And again, do that. In that case, answer will be M minus 2. So I need to find length of M, all subsequences of M minus 1 subsequences, M minus 1 length based. Similarly, maybe find M minus 2 length based. And similarly, M minus 3 length based. And so and so. So you can easily see lot of permutations needed. I know there can be many of M minus 1 sequences. So total permutations will be very high. And this becomes, obviously, this is an exponentially growing problem. So this is exponentially growing problem. And this is obviously going to be a DP candidate, which is initially exponential. Can we have a DP solution? So yes, in this case, yes. And the answer yes will come once we are able to find optimal substructure and also overlapping. So we will verify these properties later, but now we will try to address the same issue. So let's go that way. So I say now, I'll try to solve it by following the step 1, where the step 1 of DP steps was characterize optimal solution or optimal structure using substructures, using optimal substructures. So we have to find effectively those substructures. And of course, if the substructures are overlapping, then we are going in the right direction. So effectively, I want that if I'm trying to solve my LCS problem for two variables X and Y of length, let's say M and N, can I solve it recursively using optimal substructures? Substructure means the same problem should be solved by a smaller length. That effectively means it should use its solution, its optimal solution will require or should use optimal solution should use LCS of the same x and y with the smaller length. X of smaller length or y of a smaller length, or maybe and also. So if I am able to plan that way, my solution works well. So I have to effectively design my first solution that way. So the solution which we just did exponentially, considering all permutations, all subsequences, in general, I'll say all possible permutations, and then finding which one is the lengthiest or which is the most lengthy or longest permutations. So if I'm talking of those alternates being followed, such solution is normally called as a brute force solution. So this word you will study or you will find it a lot of places, but such a solution is called as a brute force solution. Never efficient, very less efficient, but yes, it works. And it is the first logic which comes to our mind by considering all permutations, combinations probably. But of course, not desirable. So we want better solution. So for better solution, now our step will be, first of all, go towards finding the optimal structure using substructures. Let's go that way. So now I come to finding that same step. So I say, how to do that? That is the most important step. As last time I also said, in MCM also, we assumed that we know the K to be known. And K to be known, and at that K, we said A1 to AK will be under one parenthesis, and AK plus 1 to AN will be another parenthesis. K known to us through some maybe special powers. Same way now. Similarly, now we assume, okay, I know some K. Assume I know some K. Which K? I will relate with my problem. Assume we know some solution. We know the solution. And guaranteedly correct solution. Currently, we know. It is impossible to know. So we have assumed that we have some supreme powers, exceptional powers. Through this, guaranteedly correct solution gets known in advance. So special powers of the God are being used. If I know this, I will say, let's assume some notation and then understand. So I say, let's assume I use a capital X with M to say that it is a string consisting of X1, X2, X3, and XM as alphabets. For example, I say X8 could be B, C, B, A, B, D, C, 337, and let's say B. So this becomes X1, small x. This becomes a small x2. This becomes X8. So I mean, capital X I'm using to represent full string of some variable written here M of length M. And small xm means I'm trying to refer to one individual character alphabet. Maybe you can say xi, I will write here. So alphabet at index I in X. So X is 1 to M. So effectively Xi is either B or C or A, etc., etc. Like this I said, B is this one, C is this one, and like this. So this is what I mean to be used in these situations. Then Similarly, I say let yn be represented in the similar way. So yn has total n length characters. For example, here it could be A, C, D, B, etc., etc. So I could say y6 equal to A, C, D, B, C, A. So this is y1, this is y2, and so on. Having said that, then I say, assume you know the answer. Answer Z is known to me. So in Z also I say, Z of size K will be the answer, which means I am able to find some alphabets or some bases which are going to be the answer as a longest common subsequence. Longest common subsequence. So this I am able to find. Assume this is known. So I have to correlate ZK with my X and Y. So I say now, this is how I correlate that either I will start that some ZK is known to me, special powers. Always in every DP, you have to start assuming that you know some K and then try to characterize and then find a recursive solution. My aim is that can I reduce the size of variables X and Y with a smaller length and then solve the same problem recursively? So I say, assume ZK is known. So how ZK will come? Obviously, if it is the last matching, it will come from the corresponding Y also. So I say, if X, small xm equal to small yn, it means last character of xm matches with last character of y. If these two match equal, that will mean obviously my zk will be equal to one of these or both of these. If not, this character must be in the answer set. So we must have this. So ideally, I say if this is the best answer, this is guaranteed that if last two characters were same, my final answer will have last character as the same alphabet or same base, same biological base, DNA base. That means this is correct situation. If they two match and this match, now I can find out the solution by reducing. So I will say, if I say LCS of xm and yn was being found, and in this case, this will be equal to 1 plus LCS, where I'm saying LCS means length of the common subsequence. So if I try to find the total length 5 or 7 or 2, I'm just interested to calculate the total length first. Later, I will find out which were the alphabets or characters common. So if I'm interested to find length for some variable x and y, I said one length is guaranteed, that these two characters, so zk is guaranteedly known to us. And how to find rest? Rest zk minus 1 is to be computed. From here, where it will come? It will come from x leaving xm, means xm minus 1. And it will come from leaving yn, means y of length n minus 1. Because xm and yn are equal, they have been considered into z. So I can say this is nothing but equal to xm minus 1, comma, yn minus 1. So I can easily say that now I am able to characterize with a smaller size. But this might not be. If it is not equal, how will we solve it? So if it is not equal, my solution effectively means that it means xm is not equal to that. This effectively means xm is not equal to yn. Then obviously means zk is not equal to both of these. So there can be one case, zk, which I have found already as an answer, if it is not equal to xm, I can claim that xm will not participate in the answer. Not to be in the answer because zk is not equal. So xm can be easily ignored because yn, if zk is not equal to xm, then I can say yn is probably what we have to think of, that zk is not equal to xm. So I can say yn may be in the answer, but xm can be ignored because zk is the last character and xm is not equal to this. I know zk is the last, so xm without taking xm also still answer can be found. So if zk is not equal to xm and both are not equal, I can say length of xm and yn will be nothing but it will be equal to finding the length ignoring xm, means reducing the length of x and y remaining the original, because zk could be equal to yn and yn correspondingly might be present into the x also at the m minus first position. So that can be this. Similarly, else I can say the other case will be that will effectively mean zk is not equal to yn, because guaranteedly xm and yn are not equal. So zk could be not equal to yn. It could be even this is not equal to both, but yes, that will automatically get covered in this. So if zk is not equal to yn, it means yn is not a part of answer guaranteedly, because yn is the last character and zk is not having, and yn is not equal to the last character of x also. So it is not a part of answer. Then I can say my LCS of the same will be nothing but LCS to be found by ignoring ym. That means y's length can reduce by 1 and I can focus on this. So overall, what I say is this is effectively given as a theorem 15.1, if I remember correctly in the book. The same thing is explained with proof. So I will suggest everyone that read this from the book and understand yourself, so that theoretically why this all statements are correct, that also you understand. So having said that, I will say now, if I know all these rules, then things are simple, that I can say LCS of xm comma yn is equal to nothing but if small xm equal to small yn, then it is equal to nothing but 1 plus LCS of smaller length in both sides. If otherwise, I'm going to have this else. If else means effectively if xm is not equal to yn, obviously, then I will say if zk is not equal to xm, then answer will be LCS of x with m minus 1 and y remaining fully. Else it will be equal to LCS of x remaining fully and y remaining 1. If both will be ultimately reducing to smaller problems. But now effectively you can see overlapping solutions possible or overlapping sub-problems visible. Why overlapping? You can easily see that LCS of xm and yn minus 1 as well as LCS of xm minus 1y as well as LCS of xm minus 1 yn minus 1 all will use, say, LCS of xm minus 2 and yn minus 2 and many more like this. So repeatedly they will be generated and needed. Repeatedly needed. Hence, I can easily see this becomes an overlapping problem. And hence, it is an ideal solution for DP. So, once I know this, then I will say, now my characterization or step 1 is effectively ready, that I have reduced the structure problem of LCS into a smaller substructure, smaller sub-problem. And this is also optimal as well as recursive. all three problems which I am solving, they are smaller sub-problems and they can be solved recursively. I am using LCS to be used and to be calculated, which internally uses recursive versions of these. Knowing this, I can go towards step 2. So if I have to go towards step 2, effectively now I have to make a recursive definition. So recursive definition needed to be defined, and this will straight away come from this itself, except that I know that now I have to write, say I have LCS to be found over some size I and j, where I say this is size of x, size of variable x, and this is size of second string, that is variable y. So LCS of ij to be computed, and this is saying length of, or I say longest length of common subsequence of xi and yj, where xi means x string of length I and yj capital being used. So it means y string of length j. Now, having said that, I can say, let's define recursively. I will say LCS of ij, so can be recursively defined in some way. First, non-recursive we must have, and then recursive versions. Recursive for some if conditions. But we initially said, I know zk. I know zk, and based on that, I decided all this. In this case also, I said effectively zk to be equal to xm. But we don't have a special power. Zk is unknown to me. How to find this? So I have to find now solution that if zk is not known, no special powers, how will I solve? So I say, if I know xm and yn, they are equal, safely I can guaranteedly say zk is nothing but xm. So I can remove zk, xn directly useful. But in this case, I said zk not equal to xm, or this meant zk not equal to yn. So my zk is needed to decide this. But I say zk is not known. Then obviously answer is the way we did in MCM. Try for all k. So I will say try for all k will mean forget about zk, think of this to be used, this also to be used, and whichever is lengthier or maximum out of the two, that I will use. Meaning that I will say now it will be nothing but I will say LCS of I and j length based x and y will be, first I will say if non-recursive, if xi is equal to yj, characters are matching, last character matching, then I will say it is nothing but 1 plus LCS over length reduced for both. Otherwise, I will say there are two possibilities. One is LCS to be found with length I minus 1j. Second possibility being LCS to be found with length I and j minus 1. Like this was case m minus 1 and n, and this is the case m and n minus 1. But now because we are trying to write for different I and j, I will be writing in the program a recursive call and making loop for I and j. So I'm just using word I and j. Both to be found. So I'll say find max out of the two, because my length means it is maximum out of the two possibilities. So there are only two possibilities. Whichever is higher out of the two, that will become the corresponding length. And then I have to know the non-recursive step also. So when it will be non-recursive, if I know that, it will help me in implementing recursive definition at least. When it will be non-recursive, answer is simple. What will be the possibility that I can say this will be 0. Because one also, if the one character length was there and both match, still I can say this answer will work. So if my one of the length is 0, I can say if I equal to 0 or j equal to 0, I can guaranteedly say the length of the highest common subsequence is 0, because then one of the string is empty. One of the bases are empty. So I can say this can be non-recursive. So 0 if I equal to 0 or j equal to 0. But having said that, this directly becomes ready as a recursive definition and implementable. So recursive function is ready, and I can write something like int LCS within bracket. I can pass the length I and j. Of course, x and y also needed. So x and y can be made and parameter. X and y needed, of course. So either they can be global or parameter. So they can be also used. But for decision making, I and j are possible. And ultimately, either I will say return 0 if it is non-recursive. So for certain if, for certain other if, I will say return 1 plus LCS of I minus 1 j minus 1. Else I will say one of the cases that one of the maximum to be returned. So I'll say return maximum out of return max out of two values. One is LCS of I and j minus 1, comma LCS of I minus 1 and j. So out of these maximum to be found and that to be returned. So that can become my direct implementation for this particular situation. And using this, I can say effectively my step 2 is ready and I'm able to do the recursive solution using non-recursive steps. But then I have to go to step 3. Means bottom up I have to grow. For bottom-up growth, effectively, I say some storage of the solutions needed, or I will say storage of a sub-solutions needed, and build up your final solution or build up upper solutions using sub-solutions, using stored values. So I have to find out which value can be the non-recursive directly stored. So that is always the starting point, which can be a non-recursive value as starting. Obviously, you know the answer. I know I equal to 0 and j equal to 0, both situations are known to me. Knowing that, let's go further and solve it. So now I say, once I know all that logic, I can straight away say that LCS, earlier it was a function call, now I will make it as a 2D array. 2D array so that various LCS ij for all I and for all j we need to compute. Recall, in case of a road, I had one parameter deciding the total function's return value. So I had 1D array. In MCM also, I had 2 dimensions based on which decisions were being done and k was being found and value was being returned. So I needed a 2D array. So effectively, the parameters which are varying in the recursive calls, they decide the dimension of your storage needed. So effectively, I will say, I will need LCS array of size m plus 1 and n plus 1, where LCS with 0, 0 to m, I will need for I will be varying into range 0 to n, and j will be varying in the range 0 to n. Once I know this, I get LCS to be calculated. So I say, now I will need LCS with I equal to 0 and up to I equal to m. Similarly, j as 0, j as n. Now, which of these values are non-recursive? First of all, I said whenever I is 0, guaranteedly all these values are 0. When I is or j is 0, I can guaranteedly say all these values are 0. So I can now guaranteedly see that these values are non-recursive. Then if I want to find some value ij, say some box ij, how this value will be computed? So LCS of ij, earlier we had small brackets, and now this becomes a stored value, stored as an array. So I can directly use. Earlier, what we wrote was LCS with 2 parameters. So it was a function call, and function call effectively recursive function and 2 parameters. So during recursive call, small brackets we were using, and now when we are able to store that, we are using square bracket. And that is the way we differentiate my DP solution versus bottom solution. So if I have to calculate LCS ij, remember what we need. In one case, I needed 1 plus LCS of I minus 1, j minus 1. First case. Other case was I needed LCS of, for knowing this, I'll say first case was this. Second case was I needed LCS of I, j minus 1 or LCS of I minus 1 and j, because out of these maximum we were using. So I needed both of these to be known. So I want to ensure that whenever I'm calculating LCS ij, previous values deciding this value, previous values must have been computed. Only then I can have a bottom-up solution. Must have been computed to have a DP solution. Only then recursion and function call will be avoided. To have a DP solution, I will say all previous values needed to solve this must have been computed. So knowing this, I say ij means either I need this value, this is effectively nothing but at position I minus 1, j minus 1, or I need this value, which is I minus 1j, or I need this value, ij minus 1. So I need either this cell or this cell or this. But knowing for any ij value, only 3 cells needed, either this or this or this. So 3 previous values needed. So I can easily see that if I try to compute this value now, all 3 values are ready. After this, let's say if I try to compute this value, all 3 values are ready. Then I can compute this value, all 3 are ready, and so and so. Similarly, when I compute this value, all 3 are ready. So effectively, row-wise, all values can be generated in that order, in order left to right. And similarly for the column also. Now that becomes a sufficient way to go for the ultimate solution of a programming. So coming to the last step, I will say now I have to write the code. So I will say int, LCS, whatever parameters you require, X, Y, length, etc., etc. But then I have to do the coding. So obviously I will require one 2D array of size m plus 1. In C syntax, you will write it as this 2D array written by using two brackets, but mathematically, I just write equivalent to mathematically, we say it as LCS of m plus 1, comma n plus 1 thing. In math, mathematically, this is true. So either way we write, doesn't matter. But first thing is, what I have to do. For I equal to, let's say, 0 to m, I can easily claim LCS of I and 0 equal to 0. When I is 0, when j is 0, all values corresponding to I can be computed. Similarly, I can say for j equal to 0 to n, I can easily say LCS of 0j means effectively I equal to 0. If I equal to 0, I said return 0. Earlier I have said, my recursive definition said this. My recursive definition has said this also, and for this case also. So if any one of this is 0, answer is 0. But that becomes a starting point. In DP, I need always a starting point. Now other values to be made. I have already seen that I can go row-wise. So for I equal to 1 to m do, and then I will say within that, I will say for j equal to 1 to n, we can calculate. Every time what I have to do, compute effectively LCS of ij. And I know that LCS of ij now computed will use previous values which have been already computed. It's an array. How to do? Obviously, I will say if xi double equal to yj, effectively it means that nothing but LCS of ij will be equal to 1 plus LCS of I minus 1, j minus 1. Why I'm saying? I'm just putting the same definition which we have defined earlier. And show this, remember, if xm equal to yn, or further I said when I said that I'm going to use LCS, I said I'll use this definition to show you that I said LCS of ij equal to 1 plus this, if x I equal to this, equal to 0, if this, straight away I'm coding the same thing. This was a starting point. And now this I have coded in this form, and other is this part. Otherwise, I have to find LCS of I minus 1j. Earlier, this was a recursive call. And now I have a DP call and array based. So this is one. Else I will say my LCS of ij will be equal to, let's say, LCS of I minus 1j based on some if condition. Else it will be reverse. LCS of ij will be nothing but equal to LCS of ij minus 1. So this is going to be the overall coding. So more or less code is ready. You have to just fine tune and check that nothing remaining. Then the final question comes. So this is more or less my recursive DP solution ready, more or less. Or DP solution using bottom-up approach is ready. But step 4 effectively says that you have to find full solution, find the final solution, or I will say find the final answer also. Final answer means not only the length, but the corresponding alphabets which were common, or common subsequence also. Means, for example, I could say B, D, A, B, C could be the answer. Length is 5. So by now, length is being computed, done. This part we have done. This how to do. Obviously, I have to store those results. So one answer could be, in this case, I have to store the result, store the output. What to store? Obviously, either xi or yj is the common. So this will be the last character or first character now, and this is being computed. First character equal. So from the remaining size, it is being computed. So this is going to be the corresponding character available to me. So I can store something. You have to think of what to store and then accordingly put it in an array of characters. In book, there is a different concept used. They have used array B of a 2D array to store the results. So I'm just explaining that also, although that is not very efficient. So they have stored Bij to be equal to arrow telling that this LCS ij generated via diagonal up from diagonal up cell. Like I said, that I have this ij value to be computed. Either this will come from this cell, or it will come from this cell, or it will come from this cell. This value will come this 1 plus this value. And this will be as it is. So if it came via this, while printing my output recursively, I would like to say, use this as in MCM parenthesis was printed. I will say, while printing this result, your previous result will come from this direction. This character will obviously come as the last character which matched, but previous values recursively which were used for finding the length will be computed from diagonal upside. On the other hand, this will be vertically up if LCS of I minus 1j was used as a maximum value. It was maximum out of the two. Or it could be I and j minus 1 was maximum, was more than I minus 1j. So whatever was the case, I have one of the three possibilities. So book said in this case, store this. If I minus 1 b j used, then a book said that you can write, in this case, I minus 1 j means your upper arrow or vertical up element being used. And in this case, your left arrow being used to compute this. So I'm not going into much more detail. Program yourself to find out or to display the answer also. Display the sequence, common subsequence. And for that, use B array, Bij, and obviously Bij will tell where the previous results are available. Use the correspondingly, and obviously recursively this can be done. I would like you to try. If you are not able to do this, maybe next class I can discuss and show you for some of the solution, but you must try yourself. And once you are able to do that, probably you can easily find out the corresponding working. Finally, coming to time complexity. What will be the time complexity? So now you can easily see I had nothing but for I equal to 1 to m, and then within this I had a nesting of j equal to 1 to n, and so and so. So effectively I can say this is nothing but order of m into n. Whether you write order or you theta, so I can say this is order of mn. Other loops were parallel loops, so they will not contribute. So now you are able to compute effectively very fastly than exponential. So with this, I will stop my discussions, and we have got a better solution ready. Try this programming. Next class, we can discuss if there are any doubts. Secondly, I will give you certain exercises to be completed at your end. I say 15.2-3 and 15.2-5 on page 378 of your third edition of Corman, these are the two sub questions given over MCM. You must do this. It will help you a better understanding. Similarly, 15.4-2 and 15.4-6 on page 396 are related to LCS. And this also you must do. And one of it obviously says taking B as a 2D array was less efficient. And can we have a better solution? Obviously, you can easily smell the solution that why to store a full 2D array. Simply, we needed the common alphabets. Storing all required alphabets will require only one array where all k characters which will match can be found. So probably I can have the common subsequence array, ultimately something like say k size and or k plus 1 size, where you could say answer is, let's say, B, D, B, A, C, something like this. So this is the common one. Storing this requires a 1D array probably. So that can be the way you can think of, but try this all once you are clear about basic LCS. So aim to implement DP solution of LCS and then solve and then print the result also. Result using B2D array. And then later stages, improve that to have 2D array replaced with 1D array. Improve B to be changed to 1D. Having said that, I would like to stop now. Bye-bye. All the best to all of you. Let me just stop.